Section 4.3, example 4, on page 259, we have you can write the polynomial function in problem 3 in a factored form as f of x equals x plus 2, x minus 2, x minus 3, and g of x equals x plus 2 squared times x minus 2 times x minus 3. In g of x, the repeated linear factor x plus 2 makes negative 2 a multiple 0. In particular, since the linear factor x plus 2 appears twice, you can say that negative 2 is a 0 of multiplicity 2. In general, a is a 0 of multiplicity n, means that x minus a appears n times as a factor. On page 260, we have if a is a 0 of multiplicity n in the polynomial function y equals p of x, then the behavior of the graph at the x-intercept a will be close to linear if n equals 1, close to quadratic if n equals 2, close to cubic if n equals 3, and so on. Example 4 says, what are the zeros of f of x equals x to the fourth minus 2x cubed minus 8x squared? What are their multiplicities? How does the graph behave at these zeros? The first thing we want to look at is what each of these terms have in common. So here we have 4 x's, here we have a 2 and 3 x's, and here we have an 8 and 2 x's. The only thing all three of them had in common were x's, and that would be 2 x's. So I can take x squared out of each of these. This gives us f of x equals x squared times x squared minus 2x minus 8. Now, inside the parentheses, we have a quadratic expression that we can factor using the x box. In order to get negative 8 when we multiply and negative 2 when we add, we can use the numbers 4 and 2, and because they're going to be negative, we need one negative. So we could use negative 4. Negative 4 times 2 is negative 8. Negative 4 plus 2 is negative 2. So in our box, we have x squared, our constant of negative 8, and then we have negative 4x and 2x. Looking at what these two have in common, x squared and 2x both have an x. To get x squared from x, we multiply by x. X times negative 4 gives us negative 4x. Negative 4 times 2 gives us negative 8. So we have f of x equals x squared times x minus 4 times x plus 2. Notice x squared we can rewrite as x minus 0 squared because x minus 0 is still x, so that's x squared. Now, we can use the zero product property to separate each of these because one of these must be 0 in order to find our zeros. We can just set everything equal to 0. So x minus 0 is the same as x, so I can say x equals 0, or x minus 4 equals 0, or x plus 2 equals 0. To solve for the 2 at the end, we can add 4 here to get x equals 4, subtract 2 here to get x equals negative 2. X equals 0 is already solved, so we have x equals 0, x equals 4, or x equals negative 2. Going back to f of x equals x squared times x minus 4 times x minus 2, we can see that we have a 0 of 0, and that was squared, so it's got a multiplicity of 2. Whereas x minus 4 was just one time, so we have a 0 of 4 with a multiplicity of 1, and similarly x plus 2 was only there once, so we have a 0 of negative 2 with a multiplicity of 1. Now just looking at the multiplicities, our graph should look somewhat like a parabola at 0, and then because we have a multiplicity of 1 for the following 2, we should have something that looks somewhat linear at 4 and negative 2. This is shown pretty well on the next slide. So here is a graph that we can examine. Notice it didn't actually ask you to graph, so you didn't have to graph this by hand. You can just look at a digital graph on Desmos, your graphing calculator, or on this slide. So notice at negative 2, it resembles a line. However, at 0, it's got this parabola shape occurring. And then back at 4, it looks very linear again. Now, something to point out about that is when we had a multiplicity of 2, notice it kind of bounced off, whereas when we had a multiplicity of 1, it crossed through the axis. So that's another thing to look at. I would now like you to find the zeros of the following function and state the multiplicity of multiple zeros. So y equals x plus 1 squared times x minus 1 times x minus 2. Now this one's already factored for you, so it's a little bit easier to find the zeros, and then you can check the multiplicities.